You are standing on a cold street before dawn, and the white cone above the dark trees looks too calm to ever hurt anyone. Mount Rainier is the quiet giant over Washington, older, wetter, and more fragile than most people realize. What happens on that mountain matters because one wrong read of its signals can turn beauty into panic, or worse, make real danger arrive while people are still relaxed. Stay with this channel for clear science told simply, and you will know what the next scary volcano headline actually means before it reaches everyone else. From far away, Rainier can feel less like a volcano and more like a piece of weather. It is the mountain on postcards, the shape behind city skylines, the bright wall on a clear day. People wave at it from freeways, photograph it from ferry decks, and then go back to normal life. That is part of why this story is so easy to miss. The snow is the trick. Snow softens the mountain in the mind. It makes the summit look clean, quiet, almost harmless. But that white cap is not just winter beauty. It is stored water, stored weight, and stored trouble. And now the words increased volcanic activity are moving around again, fast and loud. They sound like a switch has been flipped. They sound like a countdown has started. They make people picture fire at the top, ash in the sky, and red lines racing down a screen. But Rainier's real danger is stranger than that, and far more important. To see why this matters, we need to step back. Most people think volcano danger begins when a mountain starts acting obviously wild. They picture more earthquakes, rising gas, swelling ground, and then, if things get bad enough, an eruption. And if no eruption seems close, they assume the worst is still far away. Rainier has trained people to think this way because it does not behave like the volcano in a disaster movie. It has not produced a significant eruption in the past 500 years, which is long enough for whole towns, roads, habits, and generations to grow comfortable beneath it. The mountain becomes scenery. It becomes background. It becomes the thing you trust because it has been there every day of your life. But Rainier is not just a mountain. It is an active volcano, built layer by layer over a very long time. The U.S. Geological Survey says it has behaved much the same over the last 500,000 years. That means erupting, growing, breaking, and collapsing are not strange exceptions in its story. They are its story. Its size alone changes the way danger works. Rainier rises to 4,392 meters, or 14,411 feet. It is tall enough to make its own weather. It is steep enough to send loose rock, water, and ice downhill with terrible speed. And because it stands above valleys that feed into busy communities, anything that starts high can reach human life fast. Then there is the ice. USGS says Mount Rainier has 25 major glaciers and holds more than 5 times as much snow and ice as all the other Cascade volcanoes combined. That sounds like a geography fact. It is really a hazard fact. If only a small part of that snow and ice melts or gets mixed into collapsing rock, the mountain can make huge mudflows called lahars, which are fast rivers of water, ash, rock, and broken ice. Lahar is a short word for a horrible thing. Scientists often compare it to flowing concrete. That is useful because it moves like a liquid but hits like a wall. It can bury roads, smash bridges, carry logs like toothpicks, and fill valleys with mud and debris. You do not need to be on the volcano to be in its path. You only need to be downstream. This is where Rainier becomes different from the volcano most people imagine. The main fear is not lava creeping through neighborhoods. USGS says the greatest hazard from Mount Rainier is lahars, not the glowing stuff on posters. Not the big ash cloud alone. The biggest danger is heavy, fast, dirty flow moving where people already live, and a lot of people do live there. The Washington Military Department says more than 150,000 people live on former lahars in river valleys below the volcano. That phrase matters, former lahars. In other words, many homes, schools, roads, utilities, and businesses now sit on land shaped by the same kind of flows scientists worry about today. The ground itself is a record of the danger. Rainier is also weaker than it looks. Inside the mountain, hot fluids and gases have changed some rock into slippery clay-rich material. Scientists call that hydrothermal alteration. In plain English, parts of the volcano have been cooked and softened from the inside. From a distance, the peak looks hard and fixed. Inside, some sections are less like solid stone and more like a cracked wall with wet mortar. That weakness matters because steep slopes and weak rock do not wait politely for a dramatic eruption. USGS says landslides and rockfalls are potential hazards at Mount Rainier for exactly this reason. The mountain is shaken by earthquakes, it is soaked by snow and meltwater, it is cut by glaciers, it is, in a very real way, always being worked on by gravity. Still, if you live near a volcano, you want one comforting thought. You want to believe that bad things will announce themselves, and in many cases that is not foolish. USGS says a new eruption at Rainier would likely be preceded by days to months of small earthquakes beneath the mountain, subtle swelling of the volcano, and increases in volcanic gas and temperature. That is the version people hold on to. The instruments will see it. The experts will warn us. There will be time. There are good reasons people trust that picture. Earthquakes near Rainier are watched continuously by the U.S. Geological Survey and the Pacific Northwest Seismic Network, which is part of the University of Washington. In a typical year, the network detects a few hundred earthquakes at or near the volcano. That is more than any other Cascade volcano except Mount St. Helens. Rainier is not ignored. It is watched all the time. The mountain is watched in other ways too. USGS has described hydrothermal monitoring sites around Rainier, including places like Paradise Warm Springs, Paradise Creek, and the Nisqually River. Scientists track temperature, water chemistry, and flow. On the summit, gases from fumaroles, which are hot gas vents, have been sampled for decades. The point of all this is simple. Build a baseline now, so odd behavior stands out later. That baseline can save lives. If a volcano starts doing something unusual, a good baseline tells scientists whether the mountain is truly changing or whether nature is just being noisy in ordinary ways. Because mountains are noisy. Snow shifts, water moves, antennas ice over, signals flicker. A volcano can look busy on a screen and still be doing nothing new at all. But that is not how most people picture danger. Most people picture one chain. More activity means more unrest. More unrest means eruption, and eruption is the thing that matters most. By the end of this setup, that idea can feel almost solid. The mountain wakes up, instruments catch it, and the real threat begins at the summit. But that picture is about to change. What we have just taken for granted turns out to be only the neat version, the version that fits a headline and a clean warning timeline. Rainier keeps a messier truth beneath the snow, and once you see it, the whole mountain looks different. Write the moment your old picture of this volcano cracked in the comments. That one sentence helps us see which assumptions deserve the next deep dive on this channel. The reveal begins with a quiet correction. The expected story is simple. If Rainier becomes more active, the mountain's danger rises because an eruption may be getting closer. The actual story is harder and more unsettling. At Rainier, the worst danger is not always the same thing as the clearest volcanic unrest. That is the door we have to walk through now. Start with the earthquakes, because that is where fear usually starts. People expect earthquakes near a volcano to be a kind of countdown clock. More shaking means the mountain is winding up. That is the mental picture. But USGS says not all earthquakes at Rainier happen because of volcanic processes. That matters a lot. In a typical year, a few hundred earthquakes are detected near the mountain. If you did not know that, a fresh swarm or a noisy graph might feel like shocking news. But the actual finding is that Rainier already produces regular seismic chatter as part of its normal life. It is less like a fire alarm that never rings, and more like a house that always settles, creaks, and shifts in small ways. Then came a perfect example of how easy it is to get this wrong. In November 2025, a national headline claimed Mount Rainier had suddenly awakened and was buzzing with almost non-stop activity. That was the expected story people instantly recognized. The mountain is waking up, the danger is rising, the big event is coming. But local experts said no. Como News reported that the Pacific Northwest Seismic Network confirmed there was no sign whatsoever of increased activity at Mount Rainier over the past several days. Doug Gibbons of PNSN said the signal being shared was most likely radio interference caused by rime ice building up on an antenna. In other words, people thought they were hearing the mountain speak. They were mostly hearing static. That surprise is worth sitting with. The expected finding was non-stop seismic unrest. The actual finding was weather messing with an old transmission system. The feeling is like mistaking a crackling speaker for a scream in the next room, and it teaches a bigger lesson. At a volcano, even the first read of the data has to be careful, local, and patient. Now move from shaky graphs to the mountain itself. Most people expect the main danger at a volcano to come from the crater down. Fire up top, ash overhead, lava on the slopes. That is the movie version. But USGS says the greatest hazard from Mount Rainier is lahars, large mudflows and debris flows that move through valleys below the volcano. This is not a side note, it is the center of the story. Rainier is especially good at making lahars because it has abundant ice, abundant loose rock, abundant water, and slopes weakened by hydrothermal alteration. That combination is rare and ugly. The expected image is a cone throwing stuff outward. The actual danger often behaves more like the mountain briefly turning into a collapsing water tower full of mud and stone. Past lahars at Rainier were not small. USGS says some moved as fast as 70 to 80 kilometers per hour, or 45 to 50 miles per hour. Near the volcano, where valleys squeeze the flow, they were as much as 150 meters, or 490 feet, deep. Try to picture that. The expected danger is a distant rumble at the summit. The actual danger can be a fast wall of slurry deeper than many buildings are tall, charging down a valley people use every day. And here comes the sharpest turn in the whole story. Many people expect a major volcanic hazard to give off warning signs first. Earthquakes, gas, swelling ground, maybe even steam bursts. And USGS does say a future eruption would likely be preceded by days to months of such changes. That part is real. But USGS also says something far less comforting. Lahars that begin as large landslides high on Rainier's flanks can occur without warning, meaning without precursory activity detected by seismometers or other instruments. Read that slowly. Without warning. Not because scientists are careless, not because nobody is watching, because some failures may begin as gravity and weak rock doing what gravity and weak rock do. Soon after that point, the story stops being about classic eruption fear and becomes about terrain, timing, and consequence. USGS modeling using a tool called D-Claw looked at what happens if a clay-rich landslide high on Rainier transforms into a mobile lahar. The expected result might be a damaging but local event near the mountain. The actual result is worse. A slide similar in size to the electron mudflow from about 500 years ago could reach populated areas in under an hour. Under an hour changes everything. It changes what a warning means. It changes what a school drill means. It changes what a bridge means, what a river valley means, what a normal weekday means. The expected danger is a long runway toward an eruption. The actual danger can feel more like learning there is a loaded slope above a road, and the road is already part of daily life. Months and years of research have kept pointing back to the same uncomfortable truth. Rainier is dangerous not because it is constantly dramatic, but because it is built in a way that stores risk quietly. Its ice is part of the risk. Its altered rock is part of the risk. Its height above radial valleys, which are valleys spreading out from the mountain, is part of the risk. Its silence is not the opposite of danger. Sometimes silence is the container that danger sits inside. That is also why the mountain can be misunderstood from both directions. One kind of mistake is panic. A scary graph appears online, and people jump straight to eruption. The other kind is drift. Because major eruption headlines are often wrong or overblown, people start to assume the mountain is basically fine. Both mistakes miss the shape of the real problem. The real problem is not one giant movie moment. It is the overlap of several facts. The mountain is active. The mountain is weak in places. The mountain is covered in snow and ice. The mountain stands above heavily used valleys. And the kinds of flows it is best at making are exactly the kinds of flows that do not care whether a person ever saw lava. In parallel, scientists have spent years trying to hear the mountain better. USGS describes hydrothermal monitoring at summit fumaroles and at lower sites where water chemistry can hint at change. From 2010 to 2013 and 2011 to 2013, instruments recorded baseline data that could be compared against future unrest. That is, slow science, not flashy science. But at a mountain like Rainier, slow science is what lets people separate signal from noise. The same logic drives seismic monitoring. USGS says that at the first sign of unusual earthquake activity, scientists from the Geological Survey and other institutions will deploy additional instruments on and around Mount Rainier. That means the system is not frozen. It can thicken around the problem. A mountain is not monitored once. It is monitored in layers, with the option to add more layers when something changes. And yet, even with all that care, there is still uncertainty. This matters, because a story that sounds too neat becomes less trustworthy. Scientists know Rainier's slopes contain weakened rock. They know collapse can happen. They know future eruptions are likely in the long run. but they do not fully agree on every detail of timing, trigger, and exact path for every future failure. Nature rarely offers that kind of clean script. A large landslide might be nudged by an earthquake, or by the slow weakening of altered rock, or by water working through the wrong place at the wrong time. USGS says it cannot rule out the possibility that altered material could collapse due to its own weakness, even without a triggering eruption or earthquake. That sentence should reset how anyone thinks about danger here. The expected story is ignition. The actual story may be failure. By now, the mountain looks different than it did at the start. Not louder exactly, more complicated. You can still imagine a future eruption with precursors, and that remains a real concern. Ash, pyroclastic flows, steam explosions, lava flows, all of that belongs in Rainier's future possibilities. But the mountain's most threatening move does not wait for the most cinematic moment. It may begin with a slope giving way. That is why USGS calls Rainier the most threatening volcano in the Cascades. Not the most famous, not the one with the freshest movie image in the public mind, the most threatening. Because threat is not only about how often a mountain erupts, it is about what kind of mountain it is, what kind of material it holds, and who lives below it. The Washington Military Department adds the human side with one hard number. More than 150,000 people live on former lahars in the valleys beneath Rainier. That means the mountain's old flows are not ancient curiosities. They are part of the floor under present life. Children grow up above buried records of earlier disasters. Cars move across them. Pipes and power lines cross them. Whole routines sit on top of old warnings. And here is where this stops being about one mountain and begins being about us. We like danger when it is obvious. We trust bright lines, loud sounds, and countdown clocks. But some of the risks that shape human life are quieter than that. They sit in the land itself. They wait inside systems we only half notice until the wrong morning arrives. Share this with one person who still thinks volcano danger starts only when lava appears. That single handoff can replace fear with a clearer map before the next headline outruns the science. If the reveal in this story is right, then the way we think about safety has to shift a little. Not into panic, into precision. The question is no longer just, is Rainier erupting soon? The question becomes, what kinds of danger does this mountain carry all the time, and how do we live wisely beneath them? That is where the next chapter of the story is already unfolding. It is happening in monitoring networks, hazard maps, emergency planning, school drills, and in the unglamorous work of helping communities understand what a Lahar warning means. The future of this story is not only scientific, it is social. It is about whether knowledge can move faster than mud. One reason this matters so much is that a real eruption at Rainier may still come with useful warning. USGS says it would most likely be preceded by days to months of small earthquakes, subtle deformation, and changes in volcanic gases and temperature. That is good news. It means the mountain is not unknowable. There are signs to watch for. There is time that can sometimes be gained. But the other reason it matters is less comforting. USGS also says some dangerous collapses may happen without those precursors. So the future is not one single clock. It is two clocks. One may tick loudly, with signals scientists can track. The other may move more suddenly, hidden inside weakened rock and steep terrain. Living well below Rainier means understanding both. That is why monitoring keeps improving. The Cascades Volcano Observatory, the Pacific Northwest Seismic Network, and partner agencies do not watch Rainier because they expect drama every week. They watch because ordinary-looking mountains can store extraordinary consequences. Como reported in 2025 that new sensors had been installed to help detect lahars and warn communities. That kind of work is easy to ignore until you imagine who those warnings are meant for. They are meant for the person driving to work through a valley town. They are meant for the kid at school practicing a route they hope never to use. They are meant for the family that thinks of the mountain mainly as beauty at the edge of the sky. This is the domestic anchor of the whole story. Volcano science is not only for summit climbers and geologists, it is for breakfast tables. Preparedness sounds boring until you need it. A hazard map is dull until you realize it shows where a fast mudflow may actually go. A siren is background noise until the day it means move now. A drill feels repetitive until your feet already know the path. The lesson of Rainier is not to stare upward all day. It is to know the terrain beneath ordinary life. The dates make this feel real. In 2019, the National Volcano Early Warning System was authorized, pushing improvements in monitoring for high-threat volcanoes in the Cascades. By November 2023, USGS had published a broad set of Rainier hazard pages explaining lava flows, ash, earthquakes, lahars, landslides, and future eruptions in plain public language. On April 15, 2026, the agency's FAQ still described Rainier as potentially the most dangerous volcano in the Cascade Range. The message has been consistent. The mountain is not forgotten. The mountain is being watched. The numbers make it feel even more real. Elevation, 4,392 meters. Glaciers, 25 major ones. Relative ice load, more than 5 times that of all other Cascade volcanoes combined. Typical annual seismicity, a few hundred earthquakes. Past Lahar speed, 70 to 80 kilometers per hour. Potential arrival to populated areas in one modeled scenario, under 1 hour. Population living on old Lahar ground, more than 150,000. As those numbers sharpen, the future question sharpens too. What should people actually look for next? First, they should watch for what the scientists watch for, not for whatever graph goes viral. Trusted notices from USGS and the Pacific Northwest Seismic Network matter more than a dramatic screenshot. Second, they should learn the difference between eruption precursors and lahar risk. Those are linked, but they are not identical. Third, they should treat place as information. If you live in a valley below Rainier, location is part of the story whether or not you think about volcanology. There are still open questions. Exactly which weakened zones on the volcano matter most in a future collapse? How much warning might some slope failures give? How will heavier rain, changing glaciers, and altered snowpack affect smaller debris flows over time? Science keeps narrowing those questions, but it does not pretend to have finished them. That honesty is a strength. It tells us where knowledge is firm and where watchfulness must stay active. And what would a future eruption mean beyond the immediate hazard? USGS says it could affect people nearby, visitors in the national park, and even aircraft overhead. It could also affect water resources, power generation, wildlife habitat, and recreation. That is the wide arc of volcanic risk. A mountain can touch aviation, rivers, tourism, roads, schools, and household confidence all at once. A single peak can reach into many systems of modern life. So the future of Rainier is not one grim prophecy. It is a long contest between careful attention and human forgetfulness. The mountain will continue to erupt, grow, and collapse over geologic time, according to USGS. That part is not really in dispute. What remains in human hands is how ready the communities below it will be when the next meaningful change begins. Preparedness is not fear. Preparedness is memory made practical. Tomorrow's clues may be small. A notice about unusual earthquakes, a new field campaign, an update about water chemistry, a new map shown at a town meeting, a siren test that sounds routine on a blue sky afternoon. These are not side stories, they are the story. Because the future rarely arrives first as a giant event, it arrives as a pattern somebody bothered to notice. Save this video and come back to it the next time Rainier makes news. That quiet habit will give you calmer instincts and better questions when the next alarm starts bouncing around your feed. What happens next will probably not look like the ending of a movie. It may look like scientists comparing fresh readings to old baselines. It may look like one more instrument added to a slope. It may look like a public notice written in careful language. And someday, if the mountain truly changes, it may look like those careful lines becoming the first draft of a warning. That is the horizon worth facing. Not because disaster is guaranteed tomorrow, and not because the mountain is secretly exploding right now. The horizon matters because Rainier is active, because its shape and ice make it unusually threatening, and because modern life has spread into the pathways of old flows. The future here belongs to the people who can hold all three facts at once. Picture a clear morning in Washington a few years from now. The summit is bright, the valleys are busy, children are at school, drivers are crossing bridges. Somewhere, a seismometer is listening. Somewhere else, water data is being checked against a baseline built years earlier. Most people will never see those screens. Their safety may still depend on them. And hold on to one image as you leave this story. A lahar modeled to reach populated areas in under an hour. Not under a day, not after a week of obvious chaos, under an hour. That single number changes the mountain from scenery into a living test of whether knowledge, trust, and preparation can outrun speed. Rainier will keep standing there, white and quiet, teaching the same lesson in the softest possible voice. The most dangerous things are not always the loudest. The future is often decided by who noticed the ground beneath the beauty, who learned the real shape of the risk, and who kept paying attention before everyone else did. And somewhere ahead, on some calm day that does not yet have a date, that attention will matter.